Google has just made one of the biggest leaps in quantum computing history. Their new Willow chip, running an algorithm called quantum echoes, completed a task 13,000 times faster than the world's most powerful supercomputer, and for the first time, the results were verifiable. This breakthrough could finally turn quantum theory into practical technology, reshaping everything from chemistry to AI. Let's explore what happened, how it works, and why it matters. At the heart of this breakthrough lies the Willow chip, Google's most advanced quantum processor yet, built with over 100 superconducting qubits and incredibly low error rates. These qubits, unlike classical bits, can exist in multiple states simultaneously, allowing them to perform complex calculations that traditional supercomputers can't handle efficiently. What truly sets Willow apart is how it combines powerful hardware with a new algorithm called quantum echoes. Instead of running meaningless random tests, the algorithm was designed to simulate real physical systems, like how molecules behave or how energy ripples through a quantum network. The process happens in three key stages. First, the chip performs a set of quantum operations, essentially evolving the system forward. Then, one qubit is slightly disturbed, triggering a ripple effect across the entire entangled network. Finally, the system is reversed back to its original state to measure how that tiny disturbance changed everything. This echo reveals how sensitive and interconnected quantum systems truly are, and doing this at scale overwhelmed even the world's fastest classical computers. Willow completed the simulation in hours, while traditional systems would take thousands of years. The most important part? The results were verifiable, meaning they can be checked and reproduced across other quantum devices. That single shift transforms this from a headline into history. It's not just fast, it's trustworthy, measurable, and meaningful. For the first time, a quantum processor didn't just claim superiority, it proved it. This achievement goes far beyond speed, it's about usefulness. For years, quantum breakthroughs have been exciting, but mostly theoretical. Now, Google's work suggests quantum computing could soon make real contributions to science and industry. Imagine being able to simulate how a drug molecule interacts inside the human body, test millions of chemical combinations virtually, or design new battery materials that store more energy and charge faster. These are the kinds of problems quantum systems like Willow can tackle, problems too complex for even the fastest classical supercomputers. But speed alone isn't the story. The ability to verify quantum results changes everything. In science, trust is power. If a quantum computer's output can be checked and confirmed, it's no longer an experimental curiosity, it's a usable scientific tool. Researchers can rely on its findings with confidence, integrating quantum data into real-world experiments, AI systems, and engineering models. This marks the moment where quantum advantage becomes quantum reliability. It bridges the gap between fascinating demonstrations and industrial applications. And it comes at a time when technology needs such breakthroughs more than ever as industries search for ways to model nature, improve energy use, and design smarter materials. What makes this especially exciting is that the foundation has been built. The hardware works, the algorithm functions, and the data can be trusted. The next step isn't theory, it's scaling. This could be the moment when quantum computing starts shaping the technologies that define the next decade. While Google's achievement is extraordinary, it's not the final chapter, it's the first real step toward useful quantum computing. The challenge now lies in scaling up. Willow has just over 100 qubits, but practical, fault-tolerant quantum computers will require thousands, possibly millions, of reliable qubits to handle full-scale industrial tasks. Building that kind of system means tackling one of technology's hardest problems, error correction. Quantum states are incredibly fragile. Even the smallest disturbance, like heat or electromagnetic noise, can collapse their delicate balance. That's why researchers are working on logical qubits, which use multiple physical qubits to form a single stable computing unit. The good news? Willow's design shows that error rates are dropping dramatically, bringing this goal closer than ever. Then there's the software challenge. Most existing algorithms aren't built for quantum platforms yet. Scientists and engineers need new programming models, compilers, and frameworks that can harness the power of quantum physics efficiently. At the same time, companies must figure out how to integrate quantum processors with classical systems, creating hybrid workflows that combine both strengths. And perhaps the biggest hurdle is expectations. Quantum computing won't replace classical computers, it will complement them. The most realistic vision is a world where quantum machines specialize in solving problems that classical ones can't, such as molecular simulations, encryption analysis, or complex optimization tasks. Google predicts the first real-world applications of this hybrid future could appear within the next 5 years. If that timeline holds, this isn't a distant dream. It's the beginning of a technological revolution. What Willow and quantum echoes represent is not just progress, but a preview of how computing itself might evolve. Google's Willow chip and quantum echoes algorithm have redefined what quantum computing can achieve, verifiable, reproducible, and exponentially faster than anything before. This is more than a lab experiment. It's a signal that quantum technology is finally crossing into real-world science. From materials to medicine, the ripple effects will be immense. The era of practical quantum computing isn't coming. It's already starting. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching, and see you next time.